Today, we'll delve into the fundamental differences between virtual machines and containers. We'll cover their architectural foundations, compare their technical features, and analyze performance and density benchmarks. We'll also examine resource efficiency, security implications, economic factors, and strategic use cases, culminating in a discussion of the prevalent hybrid deployment model. Infrastructure virtualization is a foundational technology in modern cloud and DevOps. Virtual machines and containers are the two primary approaches, both offering application isolation and improved hardware utilization. However, they operate at distinct layers of the computing stack. Our discussion will highlight their shared goals, the different virtualization layers they employ, and key aspects like architecture, performance, security models, and practical use cases. Virtual machines utilize hardware-level virtualization, where a hypervisor like VMware ESXi or Hyper-V abstracts the physical hardware. Each VM runs its own guest operating system with dedicated virtualized resources, creating a full stack from hardware to application. In contrast, containers employ OS-level virtualization, sharing the host operating system kernel. Applications within containers remain isolated through namespaces and cgroups, resulting in a lighter software stack that omits the redundant guest OS. This fundamental difference drives many of their performance and efficiency distinctions. This table provides a concise technical comparison, highlighting the practical trade-offs between virtual machines and containers. The core distinction lies in their isolation boundary, hardware level for VMs versus OS level for containers. This cascades into other features. VMs require a dedicated guest OS, leading to startup times measured in minutes and higher resource overhead. Containers, sharing the host kernel, start in seconds or less with lower overhead. VMs are hypervisor dependent for portability, while containers offer OCI image portability, enabling rapid horizontal scaling. Containers and virtual machines exhibit significant differences in performance and density. Containers offer a roughly 10-fold consolidation advantage, allowing 100, 200 plus containers on a server that might host only 10 to 15 VMs. This is due to containers sharing the host kernel, eliminating the need for a full guest OS. Consequently, containers launch in milliseconds to seconds, while VMs take tens of seconds to minutes. Their memory footprint is also vastly different, with containers adding only megabytes atop the shared kernel. Research indicates that runtime overhead, not image size, primarily dictates launch latency. Containers achieve superior resource efficiency and density by omitting a complete guest operating system, allowing more workloads on the same hardware. Regarding security, virtual machines generally maintain stronger isolation boundaries, as hypervisor escape vulnerabilities are rare and demand highly sophisticated attacks. Containers, however, share the host kernel, meaning a kernel vulnerability could have a broader impact. To mitigate this, container isolation should be reinforced with controls like CLinux, AppArmor, sandboxing such as gvisor, and robust runtime security policies. The choice between them often depends on the specific threat model and configuration requirements. Both virtualization models have experienced real, exploited boundary failures, demonstrating that isolation strength relies on patch discipline and runtime hardening. For containers, CVE 2024-21626, known as leaky vessels, allowed malicious images to escape to the host, scoring a CVSS 8.6. Similarly, CVE 2019-5736 enabled attackers to overwrite the host runc binary to gain root. On the VM side, VMware's VMSA 2025-00004 chained 0 days for guest-to-host escape, with in-the-wild exploitation observed. While VMs offer a stronger default isolation boundary, hypervisors are not immune, and containers achieve comparable isolation only through hardened runtimes and rapid patching. The density and speed advantages of containers directly translate into significant infrastructure cost savings. Higher workload packing and faster scaling reduce server count, licensing, and idle capacity. Server consolidation allows packing over 100 containers where only 10 to 15 VMs once ran, shrinking physical and cloud footprints. Faster elasticity enabled by millisecond container starts supports tight autoscaling and scale to zero, ensuring payment only for active capacity. Operational overhead is also reduced, as patching one shared host kernel is more efficient than maintaining dozens of guest operating systems. Many enterprises adopt a hybrid approach, running containers inside VMs, balancing VM-grade isolation with container density and portability for optimal cost-effectiveness. When deciding between virtual machines and containers, consider the specific use case. Virtual machines are ideal for legacy applications, environments requiring mixed operating systems, strict regulatory isolation, and multi-tenant setups where strong separation is paramount. Conversely, containers excel where speed and density are critical, such as microservices architectures, CI/CD pipelines, cloud-native applications, and environments demanding rapid scaling. These are general guidelines, and the hybrid model often combines the strengths of both technologies for optimal results. Containers and Kubernetes have transitioned from emerging technologies to mainstream enterprise standards, with adoption now accelerating into AI workloads. Production Kubernetes use rose from 66% in 2023 to 82% in 2025, with 93% of organizations actively using, piloting, or evaluating it. Cloud-native techniques are near universally adopted by 98% of organizations, with 59% reporting most development is cloud-native. The application container market reached $5.85 billion in 2024 and is projected to hit $31.5 billion by 2030. Furthermore, 66% of organizations running generative AI models leverage Kubernetes for inference, solidifying its role as a key substrate for AI infrastructure. This chart visually represents the significant growth in Kubernetes production adoption from 2023 to 2025. In 2023, 66% of organizations were running Kubernetes in production, a figure that climbed to 80% in 2024 and reached 82% by 2025. This trend, based on the CNCF Annual Cloud Native Survey, illustrates a technology moving into mainstream saturation. The rapid increase in earlier years, followed by a slight plateau, indicates that Kubernetes has become a mature and nearly ubiquitous base for modern workloads. This highlights its widespread acceptance and critical role in enterprise infrastructure. In practice, many modern enterprises embrace a hybrid reality, running containers within virtual machines. This strategy effectively pairs the robust isolation and mature management capabilities of VMs with the speed, portability, and scalability offered by container platforms like Kubernetes. This approach allows organizations to leverage the security posture and governance strengths of VMs while benefiting from the operational agility and elastic scaling of containers. Managed Kubernetes services in public clouds often implement this very pattern, combining the best of both worlds. In conclusion, virtual machines and containers are best viewed as complementary rather than competing technologies. Virtual machines provide strong isolation and operating system flexibility, while containers deliver unparalleled speed, portability, and operational efficiency. Most modern enterprise environments achieve optimal results by adopting a deliberate hybrid approach, strategically utilizing each technology where its strengths are most pronounced. The bottom line is to combine the robust isolation of VMs with the agility of containers to forge a resilient and cost-effective hybrid strategy. Our discussion today is supported by a range of credible sources, grouped here by theme. Security claims are backed by NVD CVE records, VMware advisories, and incident reports from Huntress and Snake. Performance and density figures draw from analyses by OneUptime, a 2026 Archive study on Docker startup performance, Atmosley benchmarks, and research from the University of Mazandaran. Market adoption data is sourced from the CNCF Annual Cloud Native Surveys, Octopus Deploy, and Datadog reports. We are happy to provide full links to these resources upon request. Thank you for joining this infrastructure briefing. We appreciate your time and attention as we explored these complementary technologies powering the modern hybrid enterprise.